This section evaluates the performance of MiniBatchSparsePCA, a scikit-learn algorithm used for dimensionality reduction, especially for large, sparse datasets. I'll examine how well it handles different aspects of such datasets. I find this statement true. MiniBatchSparsePCA is specifically designed to work efficiently with sparse data with many zero values, which is common in gene expression analysis. Its MiniBatch approach allows it to process massive datasets that might not fit into your computer's memory all at once, by processing the data in smaller chunks. I would say this is partially true. The _batch_size parameter in MiniBatchSparsePCA controls the size of data chunks processed in each iteration. A smaller batch size speeds up each iteration but could lead to slightly different final results because of the randomness of the mini-batch approach. The results will still be generally close, though. This is false. While MiniBatchSparsePCA aims for orthogonal principal components, meaning they are statistically independent, the mini-batch process introduces randomness, so perfect orthogonality isn't guaranteed. It's an approximation, not a precise guarantee. I consider this false. Increasing the number of components, (n_components), generally increases the explained variance, how much of the data's variation is captured. However, adding too many components might lead to overfitting, where you capture noise rather than genuine patterns in the data. I'm using MiniBatchSparsePCA, a specific algorithm in the scikit-learn library. It's designed to handle PCA, principal component analysis, on really large datasets that are mostly empty, sparse data. Think of it like a giant spreadsheet with lots of empty cells. The mini-batch part means it processes the data in smaller chunks, making it much more memory efficient. This is perfect for our giant gene expression dataset. This statement is true. MiniBatchSparsePCA is specifically built to handle sparse and large datasets efficiently. The mini-batch approach helps it avoid memory problems and works quickly. Partially true. The _batch_size parameter, which controls the size of these data chunks, directly impacts speed. A smaller batch size means faster processing per iteration but might make the results slightly less stable. The final results will be similar, but there will be small differences due to the stochastic nature of the algorithm. Think of it like taking many slightly different routes to reach roughly the same destination. False. Increasing (n_components), the number of principal components we're trying to find, usually improves how well we can explain the data variation. However, it's not guaranteed. Adding too many components can lead to overfitting. We start capturing noise instead of real patterns in the data. False. While MiniBatchSparsePCA aims for orthogonal principal components, meaning they're mathematically independent, the mini-batch approach means we don't always get perfect orthogonality. There's some randomness involved. It's like trying to perfectly arrange many objects. It's difficult to make sure everything is perfectly aligned. I'm using MiniBatchSparsePCA because I'm dealing with a massive, sparse dataset of gene expression levels. That's a lot of data. MiniBatchSparsePCA is specifically designed to handle this type of dataset efficiently. I'm going to evaluate several statements about MiniBatchSparsePCA. We're testing knowledge of how it handles sparse data, the impact of hyperparameters, like the number of components and batch size, and how it produces principal components. This is the algorithm I'm using. It's a type of principal component analysis, PCA, that's optimized for dealing with large sparse datasets. It breaks the large data into smaller, mini-batches, to process them efficiently. These are important settings for the MiniBatchSparsePCA algorithm. (n_components) determines the number of principal components I want to extract, while (batch_size) determines how many data points I use in each mini-batch during processing. My data is a sparse matrix. In a sparse matrix, most of the entries are zero. Think of a huge spreadsheet, mostly empty except for a few numbers scattered around. This is common with gene expression data. MiniBatchSparsePCA is perfect for this kind of data. After applying MiniBatchSparsePCA, I'll have a lower dimensional representation of my data. I'll have captured the most important variation in the gene expression data using fewer variables, the principal components. It makes it easier to analyze and visualize without losing too much information. This is the title, highlighting the machine learning technique and the type of data we are using. We're using MiniBatchSparsePCA, a specific algorithm designed to handle large datasets with lots of zeros, which is common in gene expression data. It's a great choice because it's super efficient. This section sets up the scenario. We have a big dataset of gene expression levels, the activity of genes, for many samples, and we want to use MiniBatchSparsePCA to reduce the number of dimensions while keeping the important information. I want to know which statements are true about using this method. This part lays out the core question, reminding us that we are dealing with a large and sparse dataset. I need to apply my knowledge of MiniBatchSparsePCA to select the correct answers. This statement says MiniBatchSparsePCA is good for our type of data. That's true because MiniBatchSparsePCA is specifically designed to handle large, sparse datasets efficiently. It's like a super-powered tool built just for this job. This is talking about the number of components we use, represented by an underscore components. Increasing this usually increases the amount of data variation we capture, but it's not always better. Adding too many components can capture noise, reducing the accuracy of the model. The batch underscore size parameter in MiniBatchSparsePCA controls how much data is processed at once. Smaller batches are faster per iteration but might lead to slightly different final results. It mainly impacts speed, not the overall outcome. This claim states the algorithm guarantees that the principal components will be orthogonal, uncorrelated. This is false because while the algorithm aims for orthogonality, the way it works, mini batches, can introduce a bit of error, so it's not perfectly guaranteed. I'm using MiniBatchSparsePCA, a technique from Sklearn, to analyze a huge dataset of gene expression information. It's designed to handle massive datasets efficiently because it processes the data in smaller chunks. This makes it ideal for my work. This is the core question of my quiz. I need to figure out which statements about MiniBatchSparsePCA are correct based on my understanding of how it works. My data contains lots of zeros, which makes it sparse. MiniBatchSparsePCA excels at dealing with this kind of data. This is the algorithm I am using for dimensionality reduction. It is a variation of principal component analysis, PCA, optimized for speed and memory efficiency when working with large, sparse datasets. This is the core goal of this process. My goal is to simplify my high-dimensional data, many genes, by identifying the most important underlying patterns, principal components. This helps me see the bigger picture and potentially make more sense of gene interactions. This parameter controls the number of principal components I want to keep after dimensionality reduction. More components capture more detail but can also lead to overfitting, which means my analysis will not generalize well to new datasets. Finding the right balance is important. This parameter controls how much data I process at one time. A smaller batch size means faster processing of each individual batch but requires more batches to process all the data, so the overall runtime could be impacted by trade-offs. A larger batch size is slower per batch but requires fewer batches, which influences the computational efficiency. It does not significantly change the ultimate results. I'm talking about the MiniBatchSparsePCA algorithm from the Sklearn library. It's a powerful tool for reducing the dimensions of large datasets, especially those that are sparse. Think of it as a way to simplify complex data while preserving the most important information. This question challenges you to test your understanding of MiniBatchSparsePCA. You'll need to figure out which statements correctly describe how this algorithm works with large, sparse datasets and its various parameters. Let's dive in. This statement is true. Exactly. MiniBatchSparsePCA is designed for efficiency with large datasets that don't fit entirely in your computer's memory because it uses small batches of data for processing. It also handles sparse data with many zeros, very effectively. This is FALSE. While increasing the number of components, n_components, which determines the number of principal components used, often increases the explained variance, it doesn't always do so. Adding too many components can lead to overfitting. Your model might fit the training data too well, but perform poorly on new data. Think of it like trying to fit a ridiculously complicated curve through a few data points. It'll fit those points perfectly but won't be useful for predicting new data. This is PARTIALLYTRUE. The batch_size parameter significantly impacts how quickly your algorithm runs. Smaller batches mean faster iterations. However, it can slightly affect the final results due to the stochastic nature of the algorithm. The final answer might vary slightly depending on which mini-batch is processed when. It's like taking many small steps versus fewer larger ones to reach the same destination. The destination will likely be similar, but the journey and time taken will differ. This statement is FALSE. Although MiniBatchSparsePCA aims for orthogonal principal components, meaning they are unrelated to each other, the mini-batch approach introduces some randomness, making perfect orthogonality difficult to guarantee. Think of it as aiming for perfect alignment, but minor imperfections creep in due to the random nature of mini-batch processing.